Welcome back, good people. So this is the second part from the previous video. And on the previous video, we spoke about the types of circuits, mainly being the series and the parallel. And I was basically discussing how important is it for you to be able to understand whether the resistors are connected in parallel or in series. So hopefully by now you understand that. If you don't, please let me know. So we also spoke about the very important in which was the three components which make up electricity, and we spoke about the current, we spoke about the voltage, and we spoke about the resistance, right? And I even went on further to give you the special triangle to say if you are looking for either one of the three, you can use this triangle, right? So, but other than that, what I want you to know is that current is actually the rate of flow of charge, right? So besides being given, obviously we know that current can be calculated by voltage divided by resistance. Let's assume that they didn't give you the voltage and you don't have the resistance, right? Because remember I told you when I first started on the previous video, I told you that electricity is basically the flow of charge, right? If there's no flow of charge, there's no electricity, right? So now I'm telling you that the rate at which that charge flows at, that is known as current, right? So basically what I'm basically saying is that when you have charge is known, we symbolize it as Q, right? So every time we say rate, it is something divided by time, right? Obviously that time has to be in seconds. So that is another formula for current, right? So if they ever ask you what current is the rate of flow of charge, right? I hope that makes sense. And obviously the charge will be in coulombs and everything. I won't put much on that one. So what we know about current so far, we know that if we have resistors connected in series, that they will have the same current, but the ones that are connected in parallel, they will divide the current, right? And then we go to the voltage, right, which is also known as the potential difference. This one is actually the work that is done per unit of positive charge, right, to move the charge from one point to another. So we are basically saying that voltage or the potential difference is the work, right, we put to move that charge. We said that electricity is the flow of charge, and we said that the rate at which that charge flows at, that is known as current. But what actually moves that charge from one point to another, that is known as voltage. I hope that makes sense. If we don't have voltage, it means we cannot move that charge. And if the charge is not moving at a certain rate, it means that we don't have current. I don't know if you understand me, right? So here we are basically saying that the work we do to move the work we do to a unit of positive charge to move it from one point to another, that is known as voltage, right? So this W is for the work that is being done, and the Q is for the charge in coulombs, right? Obviously, the work will be work is energy, so we have to be measured in joules. This one is still measured in coulombs, right? So here, what I'm trying to do is just trying to give you the definitions of what each of these components are, right? So that you understand exactly how do we come about to even get to have electricity. Let's assume that they only give you the charge, they only give you maybe that it is moving or so much energy is required to move it at a certain rate and everything. Without being given the actual values of the resistors and everything, you should be able to calculate. So hence I'm giving you these definitions. And then the last thing is the resistance. So the resistance is basically when you resist something, you're basically opposing it, right? So the resistance is basically the opposition of the flow of electrical current. We are opposing the flow of electrical current, right? So this one doesn't have any special formula, right? So this one doesn't have any special formula. We still use these formulas, but you just have to know that it is the opposition of what? Of the flow of electrical current. And I told you about resistors that are connected in parallel and the ones that are connected in series. right? So I hope that really makes sense and I'm not confusing you in any way. And obviously, another thing that is very, very important that I stressed in the previous video is knowing the difference between the EMF and the external potential difference, of which it will come in very handy when we do the internal resistance, which I will touch on it on this video. But before we can even go there, I want to make sure that you really do understand the whole thing of resistors in parallel and series, because really, if you understand that, I don't think you will have any problems in electricity, right? So what I want you to know is that, let's say, for example, we have two resistors, right? And obviously, as you can see here, that these resistors are connected in series, right? So they are connected in series. So for you to get either one of them, the total voltage that is supplied to the whole circuit, which is this circuit connected in series, it will be the sum of voltage 1 plus voltage 2. Because we know that the resistor 1 and resistor 2 cannot have the same voltage because they are in series, but they will have the same current, but they won't have the same voltage. So when we add the voltage of this resistor and the voltage of this resistor, we will get the voltage of the whole circuit, right, which will be in series, right? So situation number 2 is when you have resistors that are connected in parallel, right? So let's say we have R1, we have R2, and we connect them like this. Obviously, from that, you can tell that they are connected in parallel, right? So from there, let's assume that this one is V1, right? And this one is connected across V2. And then let's say we have the whole thing connected across V3, right? So I want to see if you really, and to make it a point that you really understand what I'm talking about. So here, what you have to know is that the voltage in parallel, what do we know about resistors that are in parallel? We know that resistors that are in parallel, they have the same voltage, but they have the different current, right? So what I want you to know is that the voltage V1 will be the same as V2. Why are we saying V1 will be the same as V2? Because these two are in parallel, right? So since they're in parallel, they will have the same voltage. I hope that makes sense. And since this voltage 3 is connected in parallel to everything, right? You can see that it is connecting the whole thing, and it is parallel to the whole thing. It will also be the same as V1 and V2, right? And everything here will be the same as the whole voltage that is supplied by the parallel circuit. I hope that makes sense, right? I will give you more examples to ensure that I'm just giving you scenarios that you might be given, right? So let me give you the last scenario. We have resistor 1, and it is connected to resistor 2, right? Obviously, you can see that they are in series, but both of those are connected to resistor 3, which is in parallel to both of them, right? You can see that these two are in series with each other, but they are parallel to this one. So let's say across this one, we have voltmeter 1. Across this one, we have voltmeter 2, right? And then we have voltmeter 3 across this one. And then the whole thing is connected to, we have voltmeter 4. Right? Yeah, we have something like that. So in this situation, we know that voltmeter 3 and voltmeter 4, voltmeter 3, this one and this one, they would be the same, right? Voltmeter 3 will be equal to voltmeter 4. Why? They are connected in parallel to each other. But you can't say voltmeter 3 is equal to voltmeter 1 or voltmeter 2. Both of these, if you combine them, they will give us 1 voltmeter, and that voltmeter will be equal to V3 because they are in parallel to each other, meaning that V3 or V4, either one of them will be equal to V1 plus V2 combined. I hope that makes sense, right? So from everything that I've given you, I'll just give you one example and then we quickly do it, the one that is similar to the one I gave in the previous video, to see if you really understand what I'm talking about. Because really good people, if you can understand these physics, that's why I'm stressing them so much. If you can understand them, everything will make sense. And another thing, you must always check with the questions that you're given. If they say the internal resistance is negligible, do we neglect it or we include it, right? That is very important. But we'll do that straight after this example I want to give you now. I really want to make it a point that you understand. But if you still don't understand, you are more than welcome to text me, right? We have resistor 1, right? And then this resistor 1 is connected to, we have resistor 2, and we have resistor 3, oh, here we have ammeter 2, V1 connected across this one, and the whole thing is A1, right? So here we have V2, right? I know you can see the whole thing, but here's the thing, right? And then I threw it too big. That V2 up there is, they tell you that it is 15 volts, right? And here they tell you this one is 3 ohms. They tell you this one is 2 ohms. And this one is actually 4 ohms, right? I'm not forgetting anything. And then the first thing they ask you to calculate is the effective resistance. Now, here's another thing. If they say calculate effective resistance, equivalent resistance, or total resistance, all of those three words mean the same thing. Don't be confused. They say calculate total resistance, effective resistance, equivalent resistance. All of them mean one thing. And what do they mean? They all mean that give us the total resistance of the whole circuit. All of the resistors you have in the circuit, add them together, give us the total. So now we know how to calculate the ones that are in parallel, and we know how to calculate the ones in series. Add them together, that is what we want, right? So don't be confused by those words. And then after calculating all of them, obviously, the first thing that you would have to do, let's check together. We can see that resistor 1 is in series, right? Here's the thing. Here's how I like to explain this thing. We have current flowing coming this way, right? Until we divide the current, we are still in series. I repeat, until we divide the current, we are still in series. So we have the current flowing coming here, it passes there, still the same current. We get here. When we get to this point, you can see that one will have current going in this direction, right? And then we'll have current going in that direction. So the moment you divide current, just know that you are now dealing with what? You are dealing with parallel resistors. The moment you divide current, you are now dealing with parallel resistors. Since we divided the current here, the current that will be on resistor 2 and the current that will be on resistor 3 will be different, because we have already divided here. We don't have to divide it equally. That depends on the ohms we have, right? If we had 2 ohms here and we had 2 ohms here, they would have the same current. But right now they don't have the same current. But all we know is that we are going to divide that current when we get to this point, right? Why? I told you already that resistors that are in parallel to each other, they are also known as current dividers. Why were we calling them current dividers? This is the reason why, because they divide the current, right? So when we share that current, when that current splits, we already know that we are dealing with what? We are dealing with resistors that are in parallel. And then that current will flow here, will flow here, and then it will come back here to this point and join again, join here, and then we continue. So meaning that the current we had here is the same as the current we will have there. This current we are going to have here will be the same as that current we are going to have there. But this current we have here, it won't be the same as the current we have there and there, because we are going to split it. It's going to travel there, and then when we get to this point, it's going to combine again, and then we're going to have the same current. So this current we have here is the same as the current we're going to have here, right? So what I'm basically trying to explain to you is that if they say to you, calculate the current of the whole circuit, the current of the whole circuit, you can calculate it from here. This is the current in parallel, right? So when they say calculate the current of the whole circuit, already we know that we've been given that voltmeter, which is across this cell, is 15 volts. So 15 volts is the one which is going to travel here, right? So we have 15 volts, we have 15 volts. I don't know if I have my red marker nearby to show you exactly what I'm talking about. Right now, you understand the difference when we're speaking about the current. Now, I want to explain it in terms of the voltage. We have the 15 volts coming, 15 volts coming, right? 15 volts coming, 15 volts coming here. And then when we get to this point, the 15 volts, we don't divide voltage, right? Because these things are connected in parallel. We divide only the current. So we know that the voltage we have in resistor 3, right? The voltage we have in resistor 3 will be the same as the voltage we have in resistor 2. I hope that makes sense and I'm not confusing you. So what we are dividing here is the current. We are not dividing the voltage. But we are not saying that this 15 volts will be the same as this one, right? V1 cannot be 15 volts. I hope that makes sense. V1 cannot be 15 volts. All right, don't be confused. Why am I saying that V1 cannot be 15 volts? Because for you to get V1, you must use the resistance of this in parallel, not this one. The resistance in parallel. Again, you want the voltmeter in parallel, the voltage in parallel. So you use these two resistors, and then you use the current that is here in resistors in parallel for you to get the voltage, right? I know that it's like I'm talking gibberish. Okay, let me try to explain everything to you, right? So the number one question is for us to calculate the effective resistance. So when we calculate the effective resistance, we see that we have 3 ohms, right? So we would have to add these ones which are in parallel to each other. And then after adding these ones, then you add them to this one. So it would look something like this. We have 1 over resistors in parallel. It's equal to 1 over, what do we have here? We have 2 ohms plus 1 over, here we have 4 ohms, right? So already we know that lowest common denominator is going to be 4. This here goes twice, multiplied by 2 there. This goes once, and you're going to have 3 over 4. But obviously we have 1 over RP. So RP is actually, the resistance in parallel is actually the inverse of everything. It's going to be 4 over 3 ohms. This is the resistance in parallel. So we want the total resistance. Total resistance is going to be the resistor in series plus the resistance in parallel. The one in series, the only one we have in series is this 3 ohms. So you're going to have 3 ohms plus 4 over 3, right? So that 3 ohms plus 4 over 3 is actually going to give you, in decimals, is going to give you 4.33 ohms. This is the total resistance we have, right? So we are done with that question. The second question wants us to calculate A1, right? I will erase here. The second question wants us to calculate A1. What is A1? All right. Now, since they want us to calculate A1, let's go back to our diagram. We now have the total resistance of the circuit, For us to calculate A1 is this here, right? So A1 is going to measure the current that is flowing here. And I told you that the current that is flowing here and the current that is flowing here is going to be the same. So meaning A1 is basically the current of the whole circuit. And for you to get the current of the whole circuit, you must use the voltage of the whole circuit. You can't use the voltage of only the resistors connected in parallel for you to get the current of the whole circuit. If you want to calculate the current of the whole circuit, you must use the voltage of the whole circuit and the resistance of the whole circuit. I hope that makes sense. So already we have 15 volts, which is the voltage of the whole circuit, and we just calculated the resistance of the whole circuit for us to try and find the current of the whole circuit, right? So what we are going to basically do, we are going to basically use the formula that I gave you, right? Isn't it that you're looking for I? I is given by what? I is given by V over R, right? So our V is the total, which is 15, and our resistance is the one which we just got of 4.33. So A1 is going to be, it's going to give us something like 3.46, right? It's going to give us something like 3.46 amperes. So this is A1, right? We know that A1 is now 3.46. We are sorted. Then the next question is asking us to calculate what is V1, right? We calculated the resistance of the whole circuit. We calculated the current of the whole circuit being A1. Now they are asking us to calculate V1. But now remember that if you look at this thing, V1 is connected in parallel. It is only the voltage of this one's in parallel. So it can be 15. It really can be 15 because V1 is not the voltage of the whole circuit. Okay. Don't be confused, right? I know that it's not making sense. So now what you're probably asking yourself is, okay, I understand V1 is not the voltage of the whole circuit and everything. So how am I going to work about this? Since we have 3.46, we know that that 3.46 is the one that will be traveling the whole circuit, 3.46. But we said when we get here, this 3.46 will split, right? How, we don't know. How much will go this side, how much will go this side? For now, we don't know. But we don't care because we know that the voltmeter V1 here is the same as the voltage of resistor 2. And we know that all in all, the current that we're going to have in these two resistors is 3.46. So why don't we use that to our advantage? We have the current, which is going to be operating here, and we have the resistance because we already calculated the resistance of the in parallel, which is 4/3. So we know that the resistance here is 4/3. We know that the current they're going to have is 3.46. So we use those two to find what is the voltage here. I hope that makes sense for people. Hopefully I'm not confusing you. So V is given by what? V is given by IR. But our I is the 3.46 because when we get here, we still have 3.46 here. And then our resistor, we don't use the resistor of the whole circuit because this is excluded. We are only focusing on, so we are going to use this 4/3, right? And then our voltage there, it's going to be 4.6, right? It's going to be 4.6 volts. So meaning V1 is 4.6, this one is also 4.6 because they are in parallel. I hope that makes sense. I really, really hope it makes sense, right? We are done with calculating what V1 is. V1 is going to be 4.6 volts. The last question is for us to calculate what is A2, right? What is A2? All right, how do we approach this question? A2, it's very, very simple. A2 is the current of resistor 2. It is not the current of resistor 3 because you know that when we get here, the current is splitting, so they won't have the same current, right? So A2 is the current of resistor 2, meaning that when we calculate A2, we won't touch resistor 3 because A2 has nothing to do with resistor 3. It is only measuring the current in resistor 2. But already we have just calculated that the voltage here is 4.6. right? And we know that the what you call the resistance here is 4/3. So will we be correct in using this 4/3? No, because if we use this 4/3, then it means we have combined the two. So instead of using 4/3, we only use 2 because we are now only calculating the current that is in resistor 2. I don't know if I'm making sense. The voltage here is the same, yes, so we will use this 4.6. We'll use this 2 as our resistance to find the current, right? So we know that current is given by what? Current is given by voltage over resistance. Our voltage is 4.6. Our resistance is 2 ohms. That is how you get the current, which is going to be 2.3 amperes. So since it's 2.3 amperes out of 3.46, right? Isn't it that when we get here, we said we have 3.46 amperes. This 3.46 we said is going to split. Now we know that 2.3 is going here. The remaining, right? If you say 3.46 minus 2.3, the remaining is the one that will be coming this side. So if they say calculate the current in resistor 1, you just say this minus that because you know that it's going to split, you get this one. You are done. Good people, hopefully by now you understand how these things work, right? I really, really hope you understand everything. If you don't, still let me know. I'll try to do a video, but I'm just doing only a lot of examples until you understand, right? So by now, what I want you to understand is Ohm's law, right? So in Ohm's law basically states that the potential difference is directly proportional to the current, right? Provided that the temperature remains constant. So what we are basically saying here is that voltage is directly proportional to current only if the temperature is constant, right? And another thing, I don't know if I told you on the previous video, but if you keep on adding resistors in series, the total resistance will increase. But if you add the resistors in parallel, the total resistance will decrease, right? And then you must know the relationship between the resistance and the current, because current is inversely proportional to resistance. If the resistance increases, the current will decrease, right? So meaning that if you have resistors connected in series and you increase the resistors, it means that the total resistance series will increase, but the current will decrease. And since the current is directly proportional to the voltage, it means that the voltage will also decrease, right? But if you are increasing the total resistance in parallel, right, we know that the total resistance will decrease. And if the total resistance decreases, the current will increase. And if the current increases, the voltage will also increase. I hope that makes sense, right? So just understand these two things. But most importantly, understand what Ohm's law states, that the potential difference across a conductor is directly proportional to the current through that conductor, provided that the temperature is constant, right? So that is what we have to know. So we have conductors that follow the Ohm's law, and then we have conductors that don't follow the Ohm's law. So conductors that follow the Ohm's law, it means that when the current increases, the voltage also increases, but the temperature doesn't change. And then for those ones which don't follow Ohm's law, it means that when the temperature increases, when the current increases or the voltage increases, also the temperature increases, right? So that is what the example of, okay, let me do this. Maybe it will just make sense, right? We have what we call ohmic and non-ohmic conductors. The ohmic conductors are the ones that follow Ohm's law, and the non-ohmic are the ones that do not follow Ohm's law, right? So we have ohmic conductors and non-ohmic conductors. The ohmic conductors obey Ohm's law, right? Regardless of all, they obey, right? They obey. These ones, they do not, right? They don't obey Ohm's law, right? So meaning that for these ones, since the voltage is directly proportional to the current, you will always have the same ratio, right? This ratio will be constant because when they increase, they both increase. When they decrease, they both decrease. But on this side, the ratio will change, right? Meaning that if the ratio changes, right, this ratio changes for non-ohmic, right? So the great example of non-ohmic I can give you that you're used to is the light bulb. You know, when you have the light bulb, if it's being you light it maybe since from the morning, you switch it on from the morning, and then you come back late, you'll find that it is really, really hot, right? So, and when you switched it on, it was not hot. Why is it now hot? Because when the voltage increases, also the current increases, the temperature doesn't remain constant. It also increases because it doesn't follow Ohm's law. So that is why you find it at high temperatures. But if something obeys ohmic, if something is an ohmic conductor, just like your nichrome wire, no matter how long there is a flow of current through it and everything, but it won't change the temperature. The temperature will be the same, right? I hope that makes sense. So another important thing that you just have to know between the two is that in terms of the graph, because in physics they like graphs, let's say they compare voltage with current. For ohmic conductors, they will have straight resistance, right? This gradient is for resistance, right? But for this one, we have voltage and we have current. The resistor will not be that straight, right? It will be like exponential kind of, right? So this is the resistance. So what I'm basically saying is that when you have the graph of voltage versus current, right, like this, the gradient is representing the resistance. I hope that makes sense. And there's no way we can keep on talking about electricity and all these things and we don't talk about power, right? Because you know that electricity has power and everything, right? So the power is basically the rate at which work is done, because we spoke about how the voltage is the work done per unit charge, right? So the moment you include work, it means power has to be there, because power is the rate at which work is done. When you are doing work, power is there, right? So if they ask you what is power, power is the rate at which work is done. So what we are basically saying is that, remember I told you that every time they mention the word rate, it means that you will have something over time, and that time will be measured in seconds. So work, the rate at which work is done, the rate at which work is done, that is power. But we have another formula for power, which is voltage multiplied by current. And then from this, you can have a lot of other formulas. So meaning that you can still calculate power if you don't have work and you don't have time, right? So please. And another thing, don't forget that power is actually measured in watts, right? It's W, so measured in watts. And then work is actually measured in joules, right? So don't confuse those two. Power is measured in watts, work is measured in joules. But from this, we know that voltage, when we want voltage is actually current multiplied by resistance, right? And then this is the I we have. So another formula is this can be I squared R. So this is another formula for power, right? So if we don't do that, also we know that when we're calculating I is given by V over R. So we can have V, and then this one is V over R, right? So this is the same as over 1. So we have V multiplied by V, which is V squared over R. So P can also be given as V squared over R. That is another formula, right? And so those are the 4 formulas you can use, right? 1, 2, 3, 4. These are the 4 formulas you can use to calculate power depending on what you have, right? I hope that makes sense. So another important thing is like the cost of electricity. They can ask you questions based on the cost of electricity. Like someone was using this much energy, blah, blah, blah. How much will the electricity cost and stuff and stuff. So I'll just give you the formula, because if you have this formula, you're sorted. Here they won't trick you in anyway. So the cost of electricity is actually given by the power, right? Now that you know what power is, you take the power that is being used and you multiply it by the time, right? How long was the electricity being used? And you multiply that by the cost per unit, right? Cost per unit you will be given, right? So here, what you must know is that here time is actually used, it's hours, it's no longer seconds. And here the power, we want it in kilowatts, right? We don't want it in watts, we want it in kilowatts. So kilo just basically means 1,000. So if they give you the watts and you want to convert it to kilowatts, you just simply divide it by 1,000. It's simple as that, right? So that these kind of questions, they're not really tricky, right? They're just straightforward. So another last thing that is important that we have to talk about is the internal resistance. Remember, I told you that the EMF is the potential difference when the circuit is open, and then the voltage is actually the potential difference when the circuit is closed, right? I explained that on the previous video. So EMF is actually the total energy that is supplied per coulomb of charge by the cell. So now, what I basically want you to understand is that every cell has what we call the internal resistance, every cell in reality. So hence I said they will tell you whether to include that internal resistance or to exclude it. But what is important here, what I want you to do, good people, is just to understand the formula. And then if you understand the basics of everything I told you, you shouldn't be having problems. Electricity really is not difficult, as a lot of people think it is. Just understand the basics. So what I'm basically saying is that EMF is basically the voltage of the external plus the voltage of the internal. Okay, wait a minute. Let's go a step back. What do you mean voltage of the external and voltage of the internal? By voltage of the internal, I mean the voltage of the cell itself. When the cell comes, it has a certain voltage. By voltage of the external, I mean the voltage that will be going to the external circuit. The voltage that is provided by the cell is not the same as the voltage that will be going to the external circuit. But if they say exclude the internal resistance, then we only have the voltage of the external. Why isn't the voltage of the internal the same as the one of the external? Because we have a resistor. The battery, when it comes, it already has certain resistance of its own. So that resistance will take some of that. So let's assume that if the cell is not connected in the circuit, it has 6 volts. And then we connect it to the circuit, so it has now 5 volts. Where did the 1 volt go? The 1 volt is used by the internal resistance, right? This 1 volt is used by the internal resistance. I hope that makes sense. Really, I hope it makes sense. So from here, we know that voltage is given by what? Voltage is given by current multiplied by resistance. So here we have the current, right, multiplied by the resistance of the external, right? I haven't changed anything because we know that voltage is given by I multiplied by R, but this is the R of the external. This one is given by I multiplied by R, which we use a little small letter r to indicate that this is the R of the cell itself. When we use capital letter R, is the R of the external. The small letter r is the R of the internal, right? So from here, you can see that mathematically we have a common factor, which is I. Because the current doesn't change whether we are in the cell or we are in the circuit. The only thing that changes is the voltage, right? Because the resistor will take some, right? It doesn't change the current. So we have the common factor, which is I, and then we'll be left with R external plus R internal, right? So this is what we have. So that is the formula for EMF. EMF is I R plus this R, right? So if they say to you, calculate the internal resistance, find the external resistance, which is the total resistance of the whole circuit, which is what we've been doing, and find the current, and then find the EMF, and then you're done, right? I hope that makes sense. And there's nothing to worry about here, nothing at all. But please let me know, right? Please let me know if you have problems with this. I'll try to find, because now the video is too long. I'll try to find a lot of examples to give you, so that everything makes sense. Or before you can even go to the examples, let me know if any of the things I said make sense, or if they don't, or which section or doesn't make sense, so that I can explain further. So that's it from me for this video. Thank you.